So, as you turn off the lights tonight, the room goes dark.
Right.
Your eyes adjust, the shadows settle, and, well, everything just feels perfectly still.
It does, yeah.
But, what if I told you that the space between you and the ceiling, like the empty air just hovering above your bed, is currently boiling with invisible mass?
It's a crazy thought.
Right. What if I told you that an endless stream of silent phantom particles is passing right through the walls, right through the blankets, and right through your body at hundreds of kilometers per second?
And leaving absolutely no trace.
Exactly, no trace at all. I mean, we go to sleep trusting the physical architecture of our rooms, but the truth is 27% of the universe is made of this hidden architecture, stuff we can't see, touch, or hear.
Yeah, it really forces a complete shift in how you perceive your surrounding.
It really does.
Because, we spend our whole lives interacting with the visible world, the things that emit or reflect light.
Right, the stuff we can bump into.
Exactly. But that visible world is just a fragile veneer. It's just a tiny fraction of what is actually out there holding the cosmos together.
Holding it all in place.
Yeah, I mean, the gravity of the unseen is really the only thing keeping the stars from just flying apart into the void.
So tonight, we are going to explore that invisible scaffolding. Welcome to a very special, profoundly quiet edition of our show.
A really relaxing deep dive.
Welcome to Orbit to Sleep. I am so glad you're here. Wherever you are listening right now, I really hope you are somewhere soft.
Somewhere warm.
Yeah, exactly.
Yep.
Pull the blankets up a little higher, let the noise of the day fade out, and just join us on this gentle journey into the deepest, quietest mystery in modern astrophysics.
It's gonna be a good one.
We're pulling from an incredible stack of sources tonight, anchoring our discussion on a highly technical 2026 academic review.
Right, the one titled Advanced Phenomenological Architecture.
Yes, that's the one. And we're combining that with a beautifully crafted cosmological sleep script.
Our entire mission for this deep dive is, to guide your incredibly curious mind through the absolute cutting edge of particle physics and cosmology.
But we're going to do it at the pace of a slow-turning galaxy.
Exactly. We're exploring the mechanics of the invisible, but, with no rush at all.
There's absolutely no test at the end of this. You don't need to commit a single equation to memory or, take any notes.
Just let the physics wash over you.
Yeah, let the facts travel toward you like light from a distant quasar. Light that has spent billions of years crossing the void, just to pass softly through the window of your room tonight.
That's a great way to put it.
So just take a slow, deep breath in.
And let it out.
Let your shoulders drop. Let's drift back to the very first whispers of this cosmic phantom.
The story begins long before we had space telescopes or subterranean particle detectors.
Right. It starts with a really simple observation of speed. Back in 1884 with William Thomson.
Better known as Lord Kelvin.
Lord Kelvin, yeah. He was delivering a series of quiet lectures in Baltimore, analyzing the velocities of stars right in our own local galactic neighborhood.
Yeah, Kelvin was looking at the kinematics of the Milky Way, utilizing what we now call the virial theorem.
Which sounds complicated, but
the concept itself is beautifully intuitive, right? When you strip away the complex calculus.
How does it work, basically?
Well, if you look at a system of objects bound together by gravity, like, say, stars swirling around the center of a galaxy, there is this intimate, inescapable mathematical relationship.
Between what?
Between the kinetic energy of those moving stars and the gravitational potential energy of the mass pulling on them.
Right.
So if you can measure how fast the stars are moving, the virial theorem allows you to calculate exactly how much mass must be present to keep them from flying out of the system.
Like, if you spin a weight on the end of a string, the faster you spin it, the more tension you need in the string to keep it from snapping.
Exactly. Gravity is the tension in the string.
So if the stars are whipping around the galactic center at these extraordinary speeds, The galaxy needs a massive amount of gravity to hold on to them.
Right. But when Kelvin actually ran the numbers, the math broke.
It just didn't add up.
No, it didn't. The visible stars, the glowing, radiating mass that astronomers could actually see through their telescopes, it just did not provide anywhere near enough gravitational tension.
The luminous mass was completely insufficient.
Completely. So Kelvin's calculations strongly suggested that many of the bodies in our galaxy must simply be dark.
They exert a gravitational pull, but they emit no light.
Right. And a couple of decades later, in 1906, the French mathematician Henri Poincaré was reviewing Kelvin's Baltimore lectures.
Poincaré was the one who translated this missing mass into the incredibly poetic phrase, matière obscure.
Dark matter.
Matière obscure. It's such a gentle, soothing phrase to carry with you as you drift off tonight.
It really is.
And for decades, this idea just floated quietly in the background of astronomy. Like in the 1920s and 30s, you had Jacobus Kapteyn and Jan Oort analyzing the galactic disk.
And later, the halo of the lenticular galaxy NGC 3115.
Right. And every time they measured stellar kinematics, they hit the exact same invisible wall.
But the anomaly didn't really break out of our local galactic neighborhood until 1933.
With the Swiss astronomer Fritz Zwicky.
Yeah, Zwicky. He aimed his instruments out into the deep dark, looking at the Coma cluster.
Which is a massive bound collection of over 1,000 individual galaxies floating roughly 320 million light years away from us.
And Zwicky applied the exact same virial theorem that Kelvin used, but on a monstrous cosmological scale.
So he wasn't just measuring the speed of individual stars anymore.
No, he was measuring the velocity dispersion of entire galaxies, all swarming around the center of the Coma cluster.
And the results were staggering, right?
Staggering. The galaxies were moving with so much kinetic energy that, well, based on the gravity provided by their luminous mass, the cluster should have torn itself apart billions of years ago.
The galaxies should have just evaporated into the intergalactic void.
Exactly. The numbers weren't just a little bit off.
Zwicky calculated that the Coma cluster needed roughly 400 times more mass than what was emitting light.
400 times. He called this invisible holding force Dunkel materie.
He knew there was a massive ghost in the machine.
He did. And the evidence just kept patiently accumulating. Like, by 1939, Horace Babcock is looking at the Andromeda galaxy.
Our neighbor.
Right. And he notes that the mass-to-light ratio actually increases the further out you go.
So the edges of the galaxy are somehow heavier than the bright, dense center.
Yeah, which makes no sense if you only count visible stars. But, observing anomalies from afar is one thing. Nailing down the undeniable proof of the invisible architecture requires extreme precision.
Which brings us to the 1970s and the legendary work of Vera Rubin and Kent Ford.
Right. Rubin and Ford utilized a newly developed, highly sensitive image tube spectrograph.
What were they looking at specifically?
They were looking at the Doppler shift of light coming from edge-on spiral galaxies.
Okay, so when a spiral galaxy rotates, one side is spinning toward us.
Yeah, spinning toward us, which compresses the light waves and shifts them toward the blue end of the spectrum.
And the other side is spinning away from us, stretching the light waves toward the red end.
Exactly. So by measuring this red shift and blue shift with unprecedented precision, Rubin and Ford could map the exact orbital speeds of the stars at varying distances from the galactic core.
So if we look at our own solar system, which follows standard Keplerian dynamics, the planets closest to the sun, like Mercury, whip around their orbits incredibly fast.
Very fast.
But the planets furthest away, like Neptune, plod along very slowly, because almost all of the mass in the solar system is concentrated right in the center, inside the sun.
Right, so as you move away from the mass, the gravitational pull drops off, and the orbital speed drops with it.
And everyone assumed galaxies would behave the exact same way.
It made logical sense. The vast majority of a galaxy's starlight, and presumably its mass, is concentrated in the bright central bulge.
So stars on the sparse, dark outer edges of the galactic disk should orbit much slower than the stars near the core.
Right. The standard models universally predicted what we call a declining rotation curve.
But when Rubin plotted the spectrographic data, the curve didn't decline.
It didn't decline at all. It stayed completely flat.
Meaning the stars at the very far, dark edges of the galactic disk were racing around at the exact same velocity as the stars near the dense core.
Yes. And under the known laws of gravity, that flat rotation curve is completely impossible.
Unless the visible galaxy is actually embedded deep inside a colossal invisible sphere of mass.
Exactly. An enormous dark halo extending far, far beyond the visible starlight.
Providing the extra gravitational pull needed to keep those fast-moving outer stars from just flinging out into deep space.
Right. And around the same time, theoretical physicists Jeremiah Oestreicher and James Peebles published calculations showing that without those massive dark halos acting as a stabilizing anchor, spiral galaxies would fall apart.
The beautiful, flat, swirling disks would be highly unstable.
Yeah, they would essentially buckle and tear themselves apart. The unseen mass wasn't just a mathematical quirk anymore.
It was the fundamental structural foundation of the universe.
It really was.
You know, when I think about this century of history, from Kelvin's quiet lectures to Rubin's spectrographs, it feels like watching individual snowflakes falling in the night.
Oh, I like that.
Each observation was so light, so easily ignored by the broader physics community at the time. But eventually, the sheer weight of those flakes triggered an intellectual avalanche.
It reveals the profound patience inherent in the scientific method, you know?
Yeah, absolutely.
For nearly 100 years, cosmologists had to simply sit in the dark with this anomaly. They didn't have the technology to solve it.
And they didn't rush to invent magical physics to make it go away.
Right. They just meticulously recorded the discrepancy over and over, passing the mystery down through generations of astronomers until the unseen became undeniable.
So if we accept that this unseen architecture is real, we have to look at the actual recipe of the universe. What exactly is sitting out there in the dark?
Well, cosmological recipe is incredibly humbling. Everything that we consider normal matter, the protons, neutrons, and electrons that make up the device you are listening to right now.
The blankets covering you.
Yeah.
The earth beneath your bed.
Every single glowing star in the night sky. All of that is called baryonic matter. And baryonic matter accounts for roughly 5% of the total mass energy density of the universe.
Just 5%. The rest is completely alien to us.
Roughly 68% of the universe is dark energy.
That's the mysterious repulsive vacuum pressure that is driving the accelerated expansion of the cosmos.
Right. And the remaining 27% is the dark matter we are discussing tonight.
Now, cosmologists classify this 27% of dark matter by its temperature. But for anyone drifting off to sleep right now, we should probably clarify that we aren't talking about temperature in the sense of a cold winter night or a hot cup of tea.
No, not at all. In the context of early universe thermodynamics, temperature is really a proxy for velocity.
So how fast it was moving.
Exactly. It describes how fast the dark matter particles were moving right after the Big Bang, during the period when they decoupled from the hot, dense plasma of normal matter and radiation.
And we broadly categorize the theories into hot, warm, and cold dark matter.
Yes.
So if the dark matter was hot, what does that mean for the structure of the universe?
Hot dark matter, or HDM, refers to ultra-relativistic particles. These particles were moving at speeds incredibly close to the speed of light in the early universe.
Like neutrinos, right?
Yeah, the standard model neutrino is the classic example of hot dark matter. But the issue with particles moving that fast is something called the free streaming length. Well, if you have tiny primordial density fluctuations, little clumps of matter that are trying to pull more mass in via gravity to start building the first galaxies, Hot dark matter particles are moving too fast to be captured.
They just stream right out of those small gravitational wells.
Exactly.
Yeah.
Effectively smoothing out or erasing any small-scale structure.
Like trying to build a delicate sandcastle while a hurricane-force wind is blowing the grains away.
That's a great analogy.
If the universe was dominated by hot dark matter, the small stuff could never form.
Precisely. A hot dark matter universe forms top-down. Unimaginably massive superstructures and vast galaxy clusters would have to form first, and only much later would they fragment into individual galaxies.
But when we look deep into the cosmos, we see the exact opposite.
We see small structures forming early.
Mhm.
So hot dark matter cannot be the primary ingredient.
Which naturally leads physicists to consider warm dark matter.
Right. Warm dark matter sits in the intermediate velocity range. The leading candidates here are hypothetical sterile neutrinos in the kilo-electron-volt mass range.
So they move slower than hot dark matter.
Yes, so their free streaming length is shorter. They would suppress the formation of the absolute smallest dwarf galaxies, but allow medium and large structures to form.
But the undisputed reigning champion of modern astrophysics, the foundation that holds up our entire understanding of the cosmos, is cold dark matter.
Yes, the lambda CDM model, where lambda represents dark energy and CDM stands for cold dark matter. It is the most successful cosmological model in history.
Because cold dark matter particles were not relativistic in the early universe. They were moving sluggishly.
Right, because they were cold and slow, their free streaming length was microscopic. This allowed them to clump together into small, dense dark matter halos very early in cosmic history.
And those slow-moving dark halos acted like gravitational seeds.
Yes, they pulled in the primordial hydrogen and helium gas to form the very first tiny dwarf galaxies.
And over billions of years, under the relentless pull of gravity, those dwarf galaxies crashed into each other, merged, and built up the massive, majestic spiral and elliptical galaxies we see today.
It is a strictly bottom-up hierarchical formation.
And for decades, if you asked a theoretical physicist what specific particle was responsible for this cold dark matter architecture, the overwhelming favorite was the WIMP.
The weakly interacting massive particle, the theoretical darling of the physics world.
So what exactly is a WIMP?
Well, WIMPs are theorized to be incredibly massive compared to normal particles, somewhere between 1 giga-electron volt and 10 para-electron volts.
But we can't see them.
Right, because they don't interact with electromagnetism. And they don't interact with the strong nuclear force either. They only feel gravity and occasionally the weak nuclear force.
And they come from a broader theory, right?
Yeah, WIMPs are deeply tied to a theoretical framework called supersymmetry, which suggests that every known particle in the standard model has a heavier, unseen superpartner.
And the lightest of these superpartners, often called the neutrino, was the perfect WIMP candidate.
Exactly. And physicists became obsessed with the WIMP because of a mathematical phenomenon known as the WIMP miracle.
Walk us through the mechanics of that miracle.
Okay, so in the intense, unimaginable heat of the very early universe, particles of all kinds were constantly colliding, annihilating into pure energy, and spontaneously materializing back into particle pairs.
It was a dense, seething thermal bath.
Right. But as the universe rapidly expanded, it cooled down, the particles spread out, and the immense kinetic energy required to create massive WIMPs dropped.
So at a specific moment, the creation of new WIMPs just stopped entirely.
Yes, while the existing WIMPs continued to find each other and annihilate.
But eventually the universe expanded so much that the remaining WIMPs were spaced too far apart to ever find each other and annihilate.
Right, they became frozen out of the thermal bath.
So they just survived.
Yeah, that process is called thermal freeze-out. The amount of WIMPs left over is the thermal relic density.
And here's where the miracle part comes in, right?
Exactly. If you sit down and calculate the theoretical annihilation cross-section of a weakly interacting particle with a mass around the electroweak scale, The mathematics spit out an exact prediction for how much of this matter should have survived the expansion of the universe.
And the theoretical number miraculously matches the exact 27% dark matter density we actually observe through telescopes today.
It's a perfect match.
Now, I have to push back on this. Whenever science starts using the word miracle, I get a little nervous.
That's completely fair.
I mean, I can completely understand why an entire generation of physicists fell in love with this theory. The math is incredibly elegant. But mathematical symmetry doesn't guarantee physical existence.
No, it doesn't.
Just because the thermal relic density calculation perfectly predicts the 27% we see today doesn't mean the WINT is real. It feels like finding a beautifully crafted brass key on the sidewalk, bringing it home, and realizing it slides perfectly into your front door.
It feels like destiny.
Yeah, it feels meant to be, but then you try to turn it and the lock doesn't budge. Are we just falling in love with a mathematical coincidence?
It is a profound debate in the community right now. To be fair to the theorists, the elegance of supersymmetry isn't just a party trick. It wasn't invented just to solve dark matter.
Right, it solves other things too.
Yeah, supersymmetry beautifully solves the gauge hierarchy problem in quantum mechanics, stabilizing the mass of the Higgs boson, and it allows the coupling constants of the strong, weak, and electromagnetic forces to perfectly unify at high energies.
It is a profoundly deep mathematical structure.
But you are absolutely right to be skeptical. The universe is under no obligation to be elegant. It does not have to conform to our aesthetic preferences for beautiful math.
It just is what it is.
Exactly. We have built detectors to search for WIMPs for decades. We have looked for the key to turn the lock. And the fact that we haven't found it yet is exactly why experimentalists have been forced to design the most extreme, impossibly sensitive laboratories ever constructed by human hands.
Because if the invisible particles aren't going to announce themselves, we have to listen harder.
We have to isolate ourselves completely.
Right. To hear something that quiet, you can't just set up a microphone on a lab bench. You have to physically hide from the radiation of the rest of the universe, which means we need to descend.
Deep down.
I want to invite you to travel with us a full mile beneath the surface of the Earth, deep into the rock of the Sanford Underground Research Facility in South Dakota.
The reason the laboratory has to be a mile underground is because of the relentless cosmic rain.
The radiation from space.
Yeah. At every moment, the surface of the Earth is being bombarded by high-energy cosmic rays. Protons and atomic nuclei violently accelerated by supernovas and active galactic nuclei across the universe.
If you place a dark matter detector on the surface, the delicate sensors would be completely blinded by the deafening noise of this cosmic radiation.
Blinded entirely. By burying the lab deep underground, the immense dense mass of the Earth's crust acts as a silent shield, absorbing the background radiation and creating an oasis of pure quantum quiet.
And down in that profound darkness sits an experiment called LUX-ZEPLIN, or simply LZ.
Yes, the core of LZ is a massive dual-phase time projection chamber.
Inside this chamber, resting in absolute freezing stillness, are 10 metric tons of liquid xenon.
7 tons of that make up the active fiducial volume in the center.
It is just a vast, perfectly pure vat of liquid waiting in the dark for a single atomic flinch. How exactly does a tank of liquid xenon catch an invisible WIMP?
It relies on the incredibly rare chance that a dark matter particle passing through the Earth happens to strike the nucleus of a xenon atom dead on.
Why xenon?
Xenon is a heavy noble gas, which is crucial because physicists are looking for something called a spin-independent cross-section.
What does that mean in this context?
In quantum mechanics, this means the probability of a WIMP interacting with the atom scales with the square of the atomic mass number. A heavy nucleus like xenon presents a mathematically larger target for the WIMP to hit.
So the WIMP hits the xenon nucleus, like a cue ball hitting the 8-ball. What happens next?
The xenon nucleus recoils. As it recoils through the surrounding liquid, It excites and ionizes neighboring xenon atoms.
And that does what?
This immediately produces by precisely measuring the time delay between the initial S1 flash and the delayed S2 flash, physicists can calculate exactly how deep in the tang the collision occurred.
And by looking at the specific pattern of light hitting the top array, they know the exact XY coordinates.
They can pinpoint the microscopic collision in three-dimensional space.
It is an absolute marvel of engineering.
Truly.
But despite that unimaginable sensitivity, in 2025, the LZ collaboration released their data after 417 live days of patiently watching and waiting.
And the result was silence.
Total silence. They found zero evidence of WIMPs in the 3 to 9 giga-electron-volt mass range.
They were able to completely rule out spin-independent interactions with cross-sections greater than 9.2 times 10 to the negative 48 square centimeters.
But in the process of listening to that profound silence, the detector picked up a different kind of whisper. They hit a milestone known as the neutrino fog.
Yes, the neutrino fog. It represents a massive, complex turning point in modern physics.
What exactly did they hear?
During that 417-day run, the LZ detector picked up a definitive signal at a 4.5 sigma statistical significance. But it wasn't a dark matter particle.
It was a detection of boron-8 solar neutrino.
Right, neutrinos coming directly from the nuclear fusion furnace at the core of our sun.
Trillions of them are passing through your body right now. But neutrinos are famously ghostly. They hardly ever interact with normal matter.
They are ghostly, but the LZ detector has reached a level of sensitivity that is almost difficult to comprehend.
How did it detect them?
It detected these solar neutrinos through a physics process called coherent elastic neutrino nucleus scattering, or CEVNS.
Coherent scattering.
Yeah. Normally, if a neutrino hits an atom, it might interact with a single proton or neutron. But in CEVNS, the quantum wavelength of the momentum transferred by the low-energy solar neutrino is actually larger than the entire xenon nucleus.
So the neutrino doesn't just bump a single proton, it essentially smacks the entire nucleus at once.
Exactly. Causing the whole atom to ring like a bell. Yes, the neutrino scatters off all the nucleons coherently, which amplifies the probability of the interaction. The xenon atom recoils, producing the S1 and S2 light signals we discussed earlier.
But there's a problem here for dark matter hunters, right?
A profound problem. The tiny recoil generated by a solar neutrino looks almost mathematically identical to the recoil you would expect from a 5 giga electron volt WIMP.
It's like standing in an immense, perfectly silent subterranean cavern, straining your ears to hear the sound of a single pin dropping on the floor.
I love this analogy.
But your microphone is so highly tuned, so unbelievably sensitive, that suddenly you can't hear the pin drop anymore because you are picking up the collective rhythmic breathing of the sun.
That is exactly it. The background noise of the universe itself has become too loud to hear the dark matter over it.
And it brings up a vital philosophical reality about the nature of a null result in experimental physics.
Yes. Spending years and millions of dollars to map out the neutrino background and find exactly 0 WIMPs in that mass range is not a failure.
It is an absolute necessity.
The universe is speaking to us through the data. It is firmly drawing a boundary and telling us exactly where dark matter isn't.
And mapping where the invisible architecture doesn't exist is the only way we will ever narrow down where it actually resides.
Future, massively scaled up iterations, like the proposed XLZD project, will combine the world's best technologies to push deep into this fog, mapping the ultimate limits of the neutrino floor.
But if these microscopic heavy collisions aren't happening deep underground in the liquid xenon, we have to radically shift our perspective.
Right.
If the particles aren't heavy like a cue ball, well, what if they are unimaginably light? What if we aren't looking for a collision at all, but rather a vibration?
We are leaving the realm of massive particles and entering the domain of the ultralight. We are talking about the axion.
Let's explore the axion.
Yeah?
Where does the theoretical need for this incredibly light particle come from? because it wasn't originally invented to solve the dark matter problem.
No, it wasn't. The axion was born out of a completely different puzzle in quantum chromodynamics, known as the strong CP problem.
What's the strong CP problem?
Well, in the standard model of particle physics, the strong nuclear force, which binds quarks together inside protons and neutrons, should mathematically allow for a violation of charge parity symmetry.
Okay, and if this violation occurred, what would happen?
The neutron should have a measurable electric dipole moment. The positive and negative charges inside the neutron should be slightly separated.
Like a tiny magnet.
Exactly like a tiny magnet. But when we actually measure the neutron in the lab, the charge is perfectly balanced.
The dipole moment is essentially zero. The math says it should be lopsided, but reality says it is perfectly spherical.
Exactly. To solve this discrepancy, physicists Roberto Pache and Helen Quinn introduced a new mathematical symmetry to the universe.
And Frank Wilczek and Steven Weinberg realized that the spontaneous breaking of this symmetry would naturally produce a new particle.
A Goldstone boson. They named it the axion.
And cosmologists quickly realized that if axions exist, they would have been produced in unfathomable quantities during the earliest moments of the Big Bang.
Right. But because their mass is so infinitesimally small fractions of a fraction of an electron volt, they wouldn't behave like the discrete heavy wimps bumping into xenon atoms.
So how do they behave?
They behave entirely differently. In quantum mechanics, a particle's de Broglie wavelength is inversely proportional to its mass and velocity.
Because axions are so incredibly light and moving relatively slowly as cold dark matter, their quantum mechanical wavelengths would be absolutely huge.
Yes, instead of a swarm of individual particles, these massive wavelengths would overlap, creating a macroscopic classical field.
If axions are the dark matter, they form an invisible quantum field that is gently oscillating throughout the entire universe,
humming at a frequency directly determined by the particle's mass.
So instead of dodging invisible heavy bullets, we are living inside a gently humming, omnipresent quantum fluid.
It's a beautiful image.
The dark matter is a fabric weaving through the room you are in right now. But how do you build an instrument to detect a humming field of nothingness?
You build the most sensitive cosmic radio receiver on Earth. Essentially, yes. The flagship experiment hunting for this field is the Axion Dark Matter Experiment, or ADMX.
And how does ADMX work?
It utilizes a resonant microwave cavity perfectly suspended inside a massively powerful superconducting magnet.
And when you say massive, we are talking about a magnetic field between 7.6 and 9.4 Tesla.
It's incredibly strong.
You put that in perspective, that is hundreds of thousands of times stronger than the magnetic field of the Earth itself. It is a terrifyingly strong magnetic environment. Why do we need that much magnetism?
Because of a theoretical physics mechanism called the inverse Primakov effect.
The inverse Primakov effect.
Yeah. The theory suggests that the axion is capable of interacting with electromagnetism, but only under extreme conditions.
Like passing through an 8 Tesla magnetic field.
Exactly. If an axion passes through this immense magnetic field, the axion can couple with a virtual photon from the magnetic field.
And then what?
It can be coaxed into converting its tiny mass directly into a single real microwave photon.
So the immense magnetic field literally forces the invisible dark matter to turn into a microscopic flash of microwave light.
Yes. And inside that magnetic field is a hollow cylindrical microwave cavity,
which is tuned to a specific frequency.
Right. If you physically tune the dimensions of that cavity so that its resonant frequency perfectly matches the specific mass of the axion you are looking for, that single generated photon will bounce around and build up power.
Ringing out.
It's the exact same physical principle as running a wet finger around the rim of a crystal glass until it hits the resonant frequency and begins to sing.
The ADMX cavity is trying to make the axion field sing.
Exactly.
But the amount of power we're talking about here, the volume of the song they're trying to listen for, is less than a yoctowatt.
A yoctowatt.
I want you to just lie back and let that word settle in your mind. Yoctowatt. A yoctowatt is 10 to the negative 24th watts.
It's unfathomably small.
It is a decimal point followed by 23 zeros and a 1. It is impossibly profoundly faint. A single dim light bulb on your porch is radiating millions of billions of billions of yoctowatts.
It's true.
How do you measure a single yoctowatt of power without the thermal heat of the room just completely drowning the signal in static?
You have to completely eliminate the thermal noise.
How cold does that have to be?
To achieve this, the ADMX resonant cavity is placed inside a dilution refrigerator. This is a complex cryogenic system that mixes two isotopes of helium-3 and helium-4.
And they mix those to cool it down.
Yeah, by forcing the helium-3 to undergo an endothermic phase transition across the mixture boundary, it aggressively absorbs heat from the surrounding environment.
Cooling the microwave cavity down to between 25 and 90 millikelvin.
Millikelvin.
That is just a tiny fraction of a single degree above absolute zero. The metal inside that detector is physically colder than the deepest, emptiest void of intergalactic space.
It has to be. And even at that temperature, standard amplifiers would add too much quantum noise to hear the axion signal.
So they use something else.
So the engineers utilize superconducting quantum interference devices, or SQUIDs.
Squids. What exactly is a squid?
A squid consists of a superconducting ring interrupted by two incredibly thin insulating layers known as Josephson junctions.
Okay, so it's an interrupted ring.
Right. According to classical physics, the electrical current shouldn't be able to pass through the insulator.
But quantum mechanics says otherwise.
Because it's a quantum system, the superconducting electron pairs literally tunnel through the barrier.
And when a photon hits it,
When a single microwave photon from the axion conversion enters the squid, its minuscule magnetic flux alters the quantum mechanical phase of the tunneling electrons, creating a measurable interference pattern.
so we are using the quantum tunneling of electrons in a metal ring sitting near absolute zero to measure the conversion of an invisible galactic field into a yoctowatt of light.
Yes, it represents the absolute pinnacle of human engineering.
It truly does. In their 2025 data run, ADMX conducted an exhaustive search, methodically scanning the frequencies between 1.1 and 1.3 gigahertz.
And the challenge only becomes more grueling as they search for heavier axion models.
Because heavier axions require scanning higher microwave frequencies.
Right, but the mathematics of a resonant cavity dictates that to achieve a higher frequency, you must physically shrink the volume of the cylinder.
And a smaller volume means fewer axions inside, which drastically reduces your already microscopic signal power.
So to fight this physics limitation, engineers are designing complex beehive geometries. Intricate arrays of overlapping coaxial cavities that all oscillate in perfect phase together. They are artificially scaling up the volume without sacrificing the high frequency.
It is exactly like slowly, patiently turning a dial on an ultra-sensitive radio, millimeter by millimeter, listening to the static, waiting for the universe's quietest station to broadcast its signal.
Patiently waiting.
But while these incredible terrestrial experiments, the underground liquid xenon vats and the ultra-cold quantum squids are searching for microscopic, ghostly interactions, maybe we need to look up.
Look to the stars.
Yeah, if we can't find these particles colliding in a laboratory, shouldn't we be looking for macroscopic collisions in space? If a whole galaxy crashes, shouldn't the dark matter crash with it?
That is exactly the logic that led astrophysicists to the most undeniable, violent proof of dark matter's physical existence.
We have to look at clashing titans. We have to look at the bullet cluster.
Yes, the bullet cluster.
Let's travel out there. This system is officially designated 1E065756, and it is located 3.8 billion light years away from Earth.
And when astronomers point their telescopes at the bullet cluster, they aren't looking at a serene, static object.
They're looking at the frozen aftermath of a cosmic car crash of unimaginable proportions.
Two massive galaxy clusters have smashed directly into each other at thousands of kilometers per second.
To understand the collision, you have to break a galaxy cluster down into its three main components.
First, you have the individual galaxies themselves, much like our Milky Way, swirling with stars.
Second, between all those galaxies, you have the intracluster, medium vast, incredibly massive clouds of superheated baryonic gas glowing as a plasma.
And third, you have the dark matter halo engulfing the entire structure.
So what happened when these two clusters collided?
When they collided, the individual galaxies behaved like two swarms of bees flying through one another.
So they didn't really hit each other.
No, the space between the stars is so vast that the galaxies mostly just sailed right past each other without physically colliding.
But the vast clouds of intracluster gas didn't have that luxury. The gas clouds were too massive, too spread out.
Exactly. The baryonic gas from the first cluster slammed directly into the gas of the second cluster.
They experienced catastrophic electromagnetic friction, a process known as ram pressure.
As the gas clouds hit, they rapidly decelerated, compressed, and heated up to millions of degrees, glowing fiercely in high-energy X-rays.
We can clearly see this violent collision zone using the Chandra X-ray Observatory. The gas essentially got stuck in the middle of the crash site.
So the physical galaxy sailed through, and the glowing gas got stuck in a hot puddle in the center.
But where did the mass go?
This is where the physics of general relativity provides the answer. According to Einstein, massive objects warp the fabric of space-time around them.
So when light from background galaxies travels past a massive cluster on its way to Earth, that light follows the curved space-time, bending and distorting.
This is called gravitational lensing.
Right. And by meticulously measuring exactly how the background light was bent, astronomers could map precisely where the actual mass of the bullet cluster was located.
And the map showed a stunning reality.
The overwhelming majority of the cluster's mass was not located in the center with the glowing collided gas.
The vast majority of the mass had sailed right past the collision zone, staying perfectly aligned with the fleeing swarms of galaxies.
Because dark matter doesn't feel friction. It doesn't interact electromagnetically. It doesn't care about ram pressure.
Precisely. The dark matter halos passed completely through one another, entirely unaffected by the violent collision of the normal matter.
It proved, beyond a shadow of a doubt, that the missing mass of the universe wasn't just some mathematical error in our understanding of gravity.
Dark matter is a distinct, non-interacting physical substance. It passed through the most violent event in the universe, like a ghost passing through a wall.
For scientists who had spent their careers arguing against dark matter in favor of modified gravity theories, the bullet cluster was a devastating, almost insurmountable piece of evidence.
Modified gravity cannot explain why the center of mass has separated entirely from the center of visible baryonic matter.
The bullet cluster is the perfect textbook example. It beautifully confirms the standard model of cold, collisionless dark matter.
But the universe doesn't always like to be a perfect textbook.
The cosmos is messy.
Very messy. And that brings us to a system called Abell 520, informally known as the train wreck cluster.
The train wreck cluster is located about 2.4 billion light years away. It is another massive, violent cluster collision, but the data here is completely anomalous.
Anomalous how?
When astronomers applied the exact same gravitational lensing techniques to map the mass of Abell 520, they found what they call a dark core.
The invisible mass had stayed with the hot gas in the center of the collision, while the individual galaxies had sailed away, effectively leaving their dark matter halos behind.
Wait, if the bullet cluster proves that dark matter is completely frictionless and sails through a crash, but the train wreck cluster shows dark matter getting stuck and tangling up in the middle of a crash like an invisible net, do we just throw the standard model out the window?
You don't throw the standard model out, but you are forced to acknowledge the immense complexity of cosmic structures.
So what's the explanation?
The leading explanation for Able 520 is that it wasn't a clean two-way collision like the bullet cluster. It was likely a much messier, complex three-way merger of clusters,
Occurring along the line of sight from Earth, which heavily skewed the gravitational lensing data.
Right. We see similar calibration issues in smaller systems too, like the ultra-diffuse galaxy Dragonfly 44.
Ah, yes. In 2016, astronomers announced that Dragonfly 44 was composed of 99.99% dark matter.
A 10,000 to 1 ratio of dark to visible matter. It made headlines as a purely dark galaxy.
But 4 years later, more precise kinematic measurements of the globular clusters surrounding the galaxy corrected the math, bringing the ratio down to a much more standard 300 to 1.
An anomaly today might just be a calibration error tomorrow.
But we cannot simply dismiss every anomaly as an observational error.
No, we can't. Some researchers look at the dark core of the train wreck cluster and wonder, what if dark matter isn't completely collisionless?
What if dark matter does interact with itself, just a little bit?
What if, under the precise right conditions, dark matter particles can bump into each other and create friction in the dark sector?
And this speculation isn't just coming from cluster anomalies. This idea of dark matter interacting with itself is actually the leading solution to a massive crisis happening right in our own cosmic neighborhood.
You are referring to the small-scale crises of the lambda CDM model.
Right. Cold dark matter is an incredibly successful theory when you zoom out and look at the universe on massive cosmological scales.
It perfectly predicts the vast cosmic web of galaxy clusters and the temperature fluctuations in the cosmic microwave background.
But when we zoom in and look at scales smaller than 1 megaparsec, basically the scale of individual galaxies and smaller, the standard model begins to fracture.
The most famous of these fractures is the cusp versus core problem.
Explain that for us.
When astrophysicists run massive neural network-driven n-body supercomputer simulations using standard, completely collisionless cold dark matter, the gravity of the particles causes them to behave in a very specific way.
They pile up.
Yes, the particles lose orbital energy and pile up densely in the exact center of galaxy.
The mathematics, specifically the Navarro-Frank-White density profile, predict a sharply rising cusp of dark matter density at the galactic core.
The closer you get to the center, the denser the dark matter should become, approaching infinity.
But when astronomers look through their telescopes at actual real-world dwarf spheroidal galaxies orbiting the Milky Way, they don't see a dense, steep cusp.
No, they measure the kinematics of the stars in the center, and they find a wide, flat core.
The dark matter is evenly spread out rather than piled up.
And that's not the only crisis. There is the missing satellites problem, where n-body simulations predict that a galaxy the size of the Milky Way should be surrounded by hundreds, if not thousands, of tiny dark matter subhalos, each hosting a dwarf galaxy.
But we only observe a few dozen.
Exactly. Furthermore, there is the too big to fail problem. The simulations predict that the largest of these unseen subhalos should be incredibly massive and dense.
So dense that they couldn't possibly fail to ignite star formation. And yet we don't see them. The dense subhalos simply aren't there.
So how do theoretical physicists resolve this? How do you take a sharp, dense cusp of dark matter and forcefully flatten it out into a wide core?
You introduce self-interacting dark matter, or SED.
This theoretical model proposes a radical shift. Dark matter is not completely ghostly to itself.
It possesses a non-zero self-interaction cross-section.
This means that if two dark matter particles pass close enough to each other, they don't just sail past like ghosts. They can literally bounce off one another, much like billiard balls.
And if they can bounce, They can transfer kinetic energy, they can transfer heat.
Exactly. So in the dense, crowded center of a dwarf galaxy, these dark matter particles are constantly bumping into each other.
The hotter, faster moving particles from the outer halo dive into the center, bump into the colder, slower particles, and transfer their heat.
This thermal scattering acts like an outward pressure, physically pushing the dark matter away from the center, preventing it from piling up into a cusp, and smoothing it out into the flat cores we observe in reality.
It is an incredibly elegant thermodynamic solution, but the theory has to walk an impossibly fine tightrope.
It does, because observations of massive galaxy clusters, like the Bullet cluster, strictly dictate that dark matter cannot interact heavily.
If dark matter particles bounced off each other frequently in a cluster collision, they would create friction, and the dark halos would get stuck with the gas.
So how can dark matter bounce around and flatten the cores of tiny dwarf galaxies, but remain completely frictionless and ghost-like when massive galaxy clusters smash together?
The answer lies in velocity.
Physicists propose a velocity-dependent cross-section. In a massive cluster collision, the dark matter particles are moving incredibly fast, thousands of kilometers per second.
At those extreme speeds, the probability of them interacting is practically zero. They fly right past each other.
But inside a tiny, quiet dwarf galaxy, the particles are moving very slowly, maybe just 10 or 20 kilometers per second. At those low speeds, their probability of interaction skyrockets.
It's like the surface tension of water. If you are standing on a high diving board and you hit the water at 80 miles an hour, it feels like concrete.
But if you ease yourself into the pool slowly, the water is soft and yielding. The interaction completely changes based on how fast you are moving.
To achieve this velocity dependence mathematically, theorists use resonant SIDM models, which introduce a dark, attractive force mediated by a new, lightweight particle, creating what is known as a Yukawa potential.
The quantum mechanics of this are fascinating. Because the dark matter particles are moving so slowly in a dwarf galaxy, their de Broglie wavelengths stretch out.
If their specific velocity precisely matches the resonant frequency of the Yukawa potential, well, the scattering cross-section explodes by orders of magnitude.
For example, a model featuring a 31.8 JeV dark matter particle exchanging a 5.7 MeV force carrier predicts a massive spike in self-interactions, specifically when the particles drift past each other at exactly 16 kilometers per second.
It's like a cosmic tuning fork. The dark matter particles spend almost their entire existence as completely aloof phantoms, entirely ignoring one another.
But if, by pure chance, two particles happen to drift past each other in the quiet core of a dwarf galaxy at exactly 16 kilometers per second,
they strike a harmonic resonance. The quantum tuning fork hums, they suddenly acknowledge each other's existence, bounce apart, and distribute heat.
yes, and that single, perfectly timed bounce alters the thermodynamic evolution of the entire galaxy.
Though it comes with a terrifying theoretical caveat, right?
It does. Recent long-term simulations show that resonant SIDM halos are susceptible to a process called gravothermal collapse.
The bouncing particles transfer heat inward, which flattens the core. But eventually, the center of the core becomes hotter than the surrounding outer halo.
Thermodynamics dictates that heat must flow from hot to cold, so the heat flow reverses.
The core begins bleeding thermal energy outward.
And without that heat pressure to support it, the core inevitably shrinks, collapsing violently back in on itself, becoming infinitely dense.
I think what makes the SIDM model so captivating is that it adds such a rich, textured character to the dark sector.
We aren't just looking at boring, invisible rocks providing dead weight.
Just as visible matter has complex chemistry, water freezing into ice, evaporating into steam, elements binding and breaking dark matter might have an equally intricate hidden life.
It might have its own internal rules, its own specific physics, its own secret thermodynamics that only activates under the perfectly quiet, slow-moving conditions of a dwarf galaxy.
It forces us to view the dark universe as dynamic rather than static. And speaking of the dynamic, hidden life of dark matter, what if that hidden life was responsible for lighting up the very first objects in the universe?
Now we are venturing into some truly mind-bending territory. To understand this, we have to look through the golden hexagonal mirrors of the James Webb Space Telescope.
The deployment of JWST has utterly revolutionized our view of the cosmic dawn. And almost immediately upon turning its mirrors to the deep dark, it delivered a profound paradox.
A program called the JWST Advanced Deep Extragalactic Survey, or JADES, started finding exceptionally bright, massive objects at extreme redshifts.
We're talking about objects with a redshift greater than 11.
Which means we are looking back in time to an era just a few 100 million years after the Big Bang. The universe was barely a toddler. The dust had barely settled.
Exactly. And according to the hierarchical bottom-up model of structure formation that relies on cold dark matter, it takes a vast amount of time for small clumps of primordial gas to merge, cool, and slowly build up massive, highly luminous galaxies.
The JWST paradox is that objects like JADES GS-SO13-0 and JADES GS-SU14-0 appear far too bright and far too massive to exist that early in the cosmic timeline.
The established math says they shouldn't have had enough time to grow that large.
Unless they aren't galaxies at all. What if that massive point of light isn't a collection of billions of normal stars, but rather a single, impossibly gigantic entity?
This brings us to the dark star hypothesis. This is an incredibly bold, paradigm-shifting alternative to the standard model of stellar formation.
Now, the name dark star is slightly misleading. It is not a star made of dark matter.
It is a star made almost entirely of primordial hydrogen and helium gas, just like the ordinary stars we see today.
But the difference lies deep in its core. A normal star is powered by nuclear fusion. The immense gravity crushes the hydrogen atoms together until they fuse into helium, releasing energy.
A dark star never ignites nuclear fusion. Instead, it is powered entirely by the annihilation of dark matter particles trapped deep within its gravitational well.
Let's break down the mechanics of how this invisible fuel actually works. I wanted to imagine a vast cloud of primordial gas in the early universe.
As this gas cloud begins to collapse under its own gravity, a process called adiabatic contraction pulls a massive amount of the surrounding dark matter directly into the center of the cloud.
If dark matter particles, like the WIMPs we discussed earlier, are their own antiparticles, then when two of them collide in that dense central core, they annihilate.
They completely destroy each other, instantly converting their mass into pure energy, emitting gamma rays, electrons, and positrons.
And that resulting burst of annihilation energy interacts with the surrounding hydrogen gas, injecting massive amounts of heat.
This heat provides an outward thermal pressure that balances against the inward pull of the gas cloud's gravity. It creates a state of perfect hydrostatic equilibrium.
The dark matter annihilation pressure acts as a stellar cushion, physically preventing the gas cloud from ever collapsing densely enough to ignite nuclear fusion.
Because it never compresses enough to trigger fusion, it remains a cool, puffy star. Its surface temperature hovers around 10,000 Kelvin.
That's relatively cool for an early star, but its physical radius is absolutely monstrous. A single dark star could have a radius extending up to 10 astronomical units.
That means a single star would be large enough to swallow our entire solar system, with its surface extending all the way out past the orbit of Saturn.
It is a behemoth of primordial gas, kept perfectly inflated by a microscopic dark matter fire burning in its belly.
And because the surface of a dark star is relatively cool, it does not emit the intense, high-energy ionizing radiation, the stellar winds, that normal supermassive stars do.
When a normal star gets too massive, its intense radiation literally blows the surrounding gas clouds away, cutting off its own food supply and strictly limiting how big it can grow.
But a dark star is gentle. It doesn't blow its food away. It can can sit there in the cosmic dawn, endlessly accreting more and more hydrogen gas, growing larger and larger for millions of years.
It can eventually become a supermassive dark star, weighing more than 1,000,000 times the mass of our sun, and shining with the sheer luminosity of 10 billion suns.
A single puffy star shining as brightly as an entire galaxy, which would explain exactly why JWST is seeing these incredibly bright, massive objects so early in the timeline.
But how do we prove it? How do we look at a bright dot in a JWST image and know it's a dark star and not a galaxy?
We look at the chemical fingerprints in the light. In 2024, researchers analyzing the spectrum of JDGSC's 14-0 detected a hypopacific tentative absorption line known as helium-2 lambda 1640.
To create that specific line, you need an environment with an ionization energy greater than 54 electron volts. Normally, you only see that kind of energy coming from the incredibly hot, violent surface of an O-type star.
But the continuous background spectrum of this object suggests a relatively cool temperature. A supermassive dark star is one of the only theoretical objects that perfectly provides this exact contradictory signature.
A cool, puffy atmosphere illuminated from within by the intense, high-energy byproducts of dark matter annihilation.
But the dark matter fuel can't last forever. What happens when the WIMPs in the core finally run out?
When the dark matter fuel is exhausted, the annihilation stops. The outward thermal pressure that has been holding up this million solar mass giant vanishes instantly.
The star loses its hydrostatic equilibrium. Because it is so unimaginably massive, it doesn't even bother with a supernova explosion.
The entire star violently and directly collapses in on itself under its own catastrophic gravity, instantly forming a supermassive black hole.
It skips the stellar life cycle entirely and just drops into a singularity.
Yes. And this perfectly resolves another glaring mystery in astrophysics: the origin of supermassive black hole seeds.
We see colossal black holes,
Right.
like the one powering the quasar U8Z1 at redshift 10, existing far too early in the universe to have grown from normal stellar collapse.
The direct collapse of a supermassive dark star provides the perfect, massive seed required to grow those early quasars.
There is such a profound, almost emotional poetry to the dark star hypothesis. For my entire life, I have thought of dark matter as just the cold, passive scaffolding of the universe.
Just the invisible beams holding up the ceiling, doing nothing but providing dead weight.
But the dark star theory suggests that the dark sector was the spark. It literally ignited the very first light in the cosmos. It kept the first behemoths inflated and glowing. It flips our entire understanding of the cosmic dawn upside down.
It is a complete paradigm shift. We're realizing that the invisible architecture is not passive. It is an active, vital participant in the creation of light.
And as we drift deeper into the theories of the dark sector tonight, the physics becomes even more wonderfully strange. We start bridging the gap between sound waves, exotic quantum chemistry, and macroscopic quantum fluids.
Let's talk about the sound waves first. Let's talk about dark acoustic oscillations.
To visualize this, we have to look back to the epoch before the cosmic microwave background was emitted, when the universe was nothing but a dense, blindingly hot plasma of baryons and photons.
In this primordial soup, gravity was desperately trying to pull the baryonic matter together into clumps. But the intense heat and radiation pressure of the photons pushed back violently.
This epic tug of war between gravity pulling in and radiation pushing out created massive propagating pressure waves, literal sound waves rippling through the plasma of the early universe.
We call these baryon acoustic oscillations.
Sound waves rolling through the fire of the Big Bang. But how does dark matter fit into this? Standard dark matter doesn't interact with photons, so it shouldn't feel that radiation pressure, right?
Exactly. Standard cold dark matter would just sit there, unaffected by the baryonic sound waves, quietly clumping together.
But the theory of dark acoustic oscillations, or DAO, suggests that the dark sector experienced its own parallel version of this tug of war.
If dark matter interacted with a theoretical particle known as dark radiation, perhaps a massless, light-speed particle entirely hidden from our standard model, that dark radiation would exert a pressure on the dark matter.
It would create distinct acoustic waves rippling purely through the invisible mass of the dark sector.
Invisible sound waves rippling through an invisible ocean.
Does that vibration actually affect the physical structure of the universe we see today?
Yes, dramatically. These dark sound waves would physically prevent the dark matter from clumping together too early.
The vibrational energy essentially shakes the dark matter apart, leaving a distinct, measurable imprint on the distribution of mass. It suppresses the formation of very small galaxies, leaving a mathematical signature in the power spectrum of the cosmos.
Cosmologists use a complex parameterization called the ethos framework, the effective theory of structure formation, to categorize these effects by measuring the exact amplitude and wave number of that first acoustic peak.
And we can actually detect the echoes of these dark vibrations.
We are actively looking for them right now. Observations of the Lyman alpha forest, which measures how the light from distant quasars is absorbed by webs of neutral hydrogen gas, have already placed strict boundaries on how strongly dark matter could have been coupled to dark radiation.
But the real breakthrough is expected from the H-ray radio telescope. H-ray is designed to map the 21-centimeter signal.
This is a highly specific, faint radio emission produced when the quantum spin of an electron in a neutral hydrogen atom flips its alignment relative to the proton.
By mapping this 21-centimeter signal across the sky, H-ray is literally mapping the exact timing and distribution of the very first structures that formed during the cosmic dawn.
If H-ray detects a specific, mathematically predicted suppression in the small-scale structure, it could be the undeniable proof of dark acoustic oscillations.
It's amazing how a subtle, invisible vibration billions of years ago can dictate the shape of the galaxies hanging above us tonight.
Furthermore, these specific models, particularly those involving stepped dark radiation, where the mass of the dark particles changes slightly over time, are being investigated as elegant solutions to the Hubble tension and the S8 tension, helping to reconcile the discrepancies in how fast the universe is expanding and how tightly matter is clustered.
But if dark matter is in a wave, or a heavy WIMP, or a dark star fuel, what if it's an atom? What if the dark sector has chemistry?
You are stepping into the realm of composite dark matter, specifically the O-helium theory. This is one of the most exotic, creative, and rigorously complex branches of astrophysics.
Instead of a single, simple, ghostly particle, the O-helium model proposes that dark matter is actually a dark atom.
The foundation of this model relies on the existence of a massive, incredibly stable dark particle that carries a double negative electric charge. We will call it the X-, particle.
Now, because it has a double negative charge, it interacts with standard electromagnetism. And in the dense, hot aftermath of the Big Bang, the universe was flooded with primordial helium nuclei, which possess a double positive charge.
Precisely. The opposite charges are violently attracted to one another. The double negative dark particle and the double positive helium nucleus lock together through standard electromagnetic Coulomb forces.
They bind perfectly to form a neutral composite atom known as O-helium. But the physics of this dark atom are entirely bizarre compared to the chemistry we know.
Walk us through the structure. How is an O-helium atom different from the atoms making up the room we are sitting in?
In a standard Rutherford Bohr atom, like the hydrogen or oxygen in our air, you have a heavy, dense nucleus in the center, and a cloud of incredibly light electrons orbiting far, far away on the perimeter.
But in the O-helium atom, the X-, dark particle is thousands of times heavier than a standard proton.
So the heavy dark particle sits perfectly immobile in the exact center, and the lighter helium nucleus essentially sits directly on top of it.
The Bohr radius, the physical size of this dark atom, is a minuscule 2 × 10⁻13 centimeters. The entire atomic structure is essentially the exact same size as the tiny helium nucleus itself. It acts like a classic Thomson-like atom.
So you have this microscopic, incredibly dense package of heavy dark matter wrapped in a skin of normal helium. Because the charges perfectly cancel out, the entire package is electrically neutral.
Which explains why it evades our detectors. It hides in plain sight, wrapped in normal matter. But what happens when this dark atom actually bumps into something on Earth?
That is where the physics of the dipole-Coulomb barrier comes into play. When an O-helium atom drifting through the galaxy happens to strike a normal atom in a subterranean detector, say a heavy nucleus of sodium or iodine, the intense localized electric field of the target atom's nucleus strongly interacts with the O-helium.
The electric field violently polarizes the dark atom. It physically pulls the positively charged helium shell away from the negatively charged dark core.
This polarization creates an electromagnetic barrier that physically prevents the helium shell from actually touching and fusing with the target nucleus.
This is a vital mathematical requirement of the theory, because if the O-helium was constantly fusing with normal matter, we would observe anomalous, impossibly heavy isotopes of elements all over the Earth's crust, and we don't.
Exactly. Instead of fusing, the target nucleus captures the entire O-helium atom into a low-energy bound state, releasing a tiny photon of energy in a process called radiative capture.
The physics of this complex dance, the polarization, the dipole barrier, the radiative capture, has been proposed as the sole viable explanation for the highly controversial De Malabre modulation signal.
DAMA is an experiment in Italy that has claimed for over 2 decades to see an annual seasonal fluctuation in dark matter hits that absolutely no other detector on Earth can replicate or verify.
The specific strange chemistry of O-helium might be the only mechanism that allows DAMA to see a signal while liquid xenon detectors see nothing.
The dark matter is literally hiding inside microscopic helium armor, behaving like a phantom atom. The creativity required to build these theories is simply staggering. It's a testament to the human desire to map the unknown.
And we are continually mapping new interactions. We are beginning to understand how this dark architecture behaves under the most extreme gravitational stress imaginable. Specifically, what happens to dark matter when it gets close to a supermassive black hole?
It creates a dark matter spike. Let's delve into the mechanics of that. Dark matter halos, the massive clouds surrounding galaxies, are generally quite smooth and evenly distributed.
But when you place a supermassive black hole in the exact center of that halo, the physics change. The immense, inescapable gravity of the black hole slowly, steadily pulls the surrounding dark matter inward over billions of years.
Because dark matter particles are largely collisionless, they can't easily shed their orbital kinetic energy. They don't crash into an accretion disk like glowing gas does.
Instead, they pile up into incredibly dense, steep, invisible formations around the event horizon, known mathematically as a dark matter spike.
And astrophysicists believe we might actually be able to hear the existence of these invisible spikes using gravitational wave observatories.
If a smaller object, like a stellar mass black hole, is caught in the gravitational pull of the supermassive black hole, it begins to spiral inward.
As it orbits closer and closer, it churns up the fabric of space-time, emitting gravitational waves that ripple out across the universe. If that smaller black hole is plunging directly through a dense dark matter spike, it experiences a phenomenon known as dynamical friction.
Think of a boat moving quickly through a calm lake. As the boat pushes forward, its gravity pulls the dark matter particles toward it, but because the boat is moving fast, the particles end up accumulating in a dense wake behind the moving black hole.
The gravitational pull from that trailing wake acts as a literal drag force, constantly pulling backward on the black hole, bleeding away its kinetic energy.
That dynamical friction causes the smaller black hole to lose energy faster than it would if it were orbiting in an empty vacuum. It spirals inward more rapidly.
When the gravitational waves finally reach our detectors on Earth, the signal arrives slightly out of sync with our standard vacuum predictions. We call this the dephasing of the gravitational wave.
But the universe is never a simple equation. The dark matter fights back against this process.
It does. Recent, highly complex hydrodynamic simulations have revealed the phenomenon of halo feedback. The smaller black hole isn't just passively suffering from drag, it is actively stirring the dark matter.
Its passage physically injects immense kinetic energy into the spike, violently heating up the dark matter particles and scattering them outward, away from the center.
This feedback mechanism drastically reduces the overall density of the dark matter spike, which in turn significantly reduces the dynamical friction drag.
The simulation suggests this chaotic dance suppresses the dephasing effect by a factor of 10 to 100. It is a violent, invisible war between the black hole's gravity and the dark matter's kinetic energy, playing out in complete silence.
Silence and extreme violence. Which brings us to our final topic tonight. We've saved the most counterintuitive and honestly, the most profoundly relaxing theory for last.
As you lie there listening, I want you to focus entirely on the word fluid. The theory of superfluid dark matter proposes that the dark matter permeating our galaxy is not made of heavy wimps bouncing like billiard balls, and it's not made of dark atoms.
Instead, it is made of ultralight bosons.
Bosons with a mass of just a fraction of an electron volt. To understand a superfluid, you must understand the dual nature of quantum mechanics. Every single particle in the universe also behaves as a wave, possessing a specific de Broglie wavelength.
The lighter the particle and the colder its environment, the longer and wider its quantum wave becomes.
If these dark matter bosons are incredibly light, and the ambient temperature of the galactic disk is sufficiently cold, their individual quantum waves begin to physically stretch out and expand until they start to overlap with one another.
And when millions of these quantum waves overlap perfectly,
they lose their individual identities entirely, they stop behaving as discrete single particles, and they condense into a single massive macroscopic quantum state known as a Bose-Einstein condensate.
The dark matter undergoes a literal phase transition. It turns into a superfluid, a frictionless quantum liquid with absolute zero viscosity, flowing effortlessly and silently through the entire galactic disk.
I love this imagery so much, especially for a deep dive designed to guide you into sleep. I want you to let go of the image of the Milky Way as a chaotic, swirling disk of dry rocks, burning gas, and dead void.
I want you to imagine the galaxy you live in as a vast, frictionless quantum ocean. And inside this ocean, the dark matter hums.
Because it is a macroscopic superfluid, it can support collective quantum excitations. It can carry sound waves. Physicists call these quantized sound waves phonons.
And here is the absolute undeniable genius of the superfluid model. These dark phonons mediate a long-range force that strictly dictates the movement of normal baryonic matter.
When ordinary stars and clouds of gas move through this quantum superfluid, the phonons pull on them, modifying the local laws of gravity in a way that perfectly mathematically mimics MEMO-ND modified Newtonian dynamics.
I want to pause here just to make sure we truly appreciate how revolutionary this synthesis is. For decades, there have been two violently warring camps in astrophysics.
On one side, you have the lambda CDM particle camp, who believe dark matter is a tangible physical substance.
On the other side, you have the MOD camp, who believe that dark matter is a myth, and that gravity simply behaves differently, changing its rules at the ultra-low accelerations found on the outer edges of galaxies.
These two theories have been bitter enemies. Superfluid dark matter takes these two opposing forces and marries them beautifully.
It perfectly bridges the gap. It provides a cohesive explanation for all scales of the cosmos. On the vast, unimaginably huge cosmological scales of galaxy clusters, like the bullet cluster we discussed, the dark matter particles are moving incredibly fast.
Their kinetic energy is high, which means their de Broglie wavelengths are short. Because the waves don't overlap, they never condense into a superfluid.
In a cluster collision, they just act exactly like normal collisionless cold dark matter. They sail right through each other, perfectly satisfying the requirements of the lambda CDM model.
But inside the cold, calm, slow-moving interior of an individual galaxy like our Milky Way, they chill, they overlap, and they condense into a superfluid.
The phonons generate the MOND-like flat rotation curves that Vera Rubin observed. It gives us the absolute best of both worlds.
And the quantum mechanics of a superfluid demand one more incredible visual. If the galaxy is a fluid and the galaxy is rotating, the superfluid must rotate with it. But a quantum fluid cannot rotate like a solid record disk.
No, quantum mechanics strictly forbids it. To shed angular momentum, a rotating superfluid must fracture into a lattice of localized tornadoes.
Tiny whirlpools of empty space known as quantum vortices. If the dark matter in our galaxy is indeed a superfluid, then the space around us, the space passing through your room, is permeated by an invisible, highly structured lattice of quantum vortices spinning silently in the dark.
Just take a slow, deep breath and let that image settle. We are floating inside that exact quantum fluid right now.
The invisible architecture of the universe is infinitely more intricate, dynamic, and beautiful than we ever dared to imagine.
And on that note, as the night deepens, it is time to gently bring our journey to a close. Let's softly recap the incredible distance we've traveled tonight.
We started with Lord Kelvin in 1884, looking at the quiet, anomalous movement of stars in a Baltimore lecture hall.
We traveled down a mile underground into the absolute quiet of South Dakota, understanding the quantum tunneling inside SQUD detectors and the microscopic recoil of liquid xenon vats.
We stood back and watched the colossal violence of the bullet cluster and the train wreck cluster, mapping the undeniable physical footprint of the dark sector.
We envisioned the cosmic dawn, where the first light of the universe was ignited by the annihilation of WIMPs inside giant, puffy, supermassive dark stars.
And we explored the absolute frontier of modern theory, where dark matter might be vibrating with acoustic pressure waves, binding into Thomson-like ohelium atoms, or flowing through our galaxy as a frictionless, phonon-generating Bose-Einstein condensate.
And the work to prove this continues tirelessly. Right now, as you rest, the ESA Euclid Space Telescope is out there in the freezing cold of space, painstakingly building an unprecedented 3D map of this invisible architecture, observing the gravitational lensing of structures like the Cat's Eye Nebula.
The LZ experiment pushes patiently onward, aiming for 1,000 live days of watching the dark.
So why does all of this matter to you? Why did we spend the last hour talking about particles and atoms and fluids that you will never be able to see or touch?
I think it matters deeply, especially tonight, because it reminds us that we live in a universe that comfortably allows for profound mysteries.
The universe does not demand that we figure everything out immediately. It is perfectly fine to lie in the dark and not have all the answers. The invisible 27% of the universe, this terror obscure, is holding your very galaxy together right now.
It is keeping the stars in their quiet orbits, keeping the Earth steady in its path, keeping everything safe, bound, and supported.
It is doing all the heavy lifting completely out of sight so that you can simply close your eyes, let go of the day, and rest.
And as you do let go, I want to leave you with one final, unmentioned thought to mull over.
What's that?
If the superfluid theory of dark matter is correct, if our Milky Way is indeed permeated by a frictionless Bose-Einstein condensate, that means right now, as you lie in bed, breathing slowly in and out, your physical body is literally submerged inside a macroscopic quantum motion.
It's an incredible thought.
Every time your chest rises with a breath, every tiny unconscious shift you make under the blankets as you drift off to sleep, you are physically displacing that fluid.
Your quietest, softest movements might be sending microscopic ripples, tiny invisible phonons, radiating outward through the unseen fabric of the cosmos.
You are not separate from the deep dark. You are physically, intimately connected to the hidden architecture of the universe.
The unseen architecture of the room hasn't gone anywhere. The walls, the ceiling, the quiet hum of the dark matter. They're all holding the space together, completely invisible in the dark.
You are held safely by the invisible architecture of everything.
Thank you for joining us on this gentle orbit. Sleep well. Have a wonderful night.